All right. So, where do we go first? Where do we go first? Hello, week 9. Program, thank you. Thank you, Luan. Program, here we are. What do we look for? Dist fill. Press enter to run it. Smallest x.
0.
Good. I want to do one step, and this you might notice this is D, E, and F. They're A, B, and C. Most of A, B, and C does get answered via this program, but the very first question in A, if I remember correctly, is identify the random variable that you're interested in, which we're going to call x. X here. What is x? What does it stand for? Say that again. Say that again.
The number of people
That say
yes.
yes. That agree in the affirmative. Out of 12, right? It's the number of folks out of 12 who say yes to the question, are you going to Tet festivities this year? Yeah, perfect. Perfect. So the least number out of 12 could be 0, because they might all say no. So go with 0, yes, smallest. Largest?
12.
Is 12, because they could all say yes as well. They could all say yes as well. Probably not that likely. Now we press enter. It's going to take a couple seconds. It's done now. In L1, 0 through 12 is listed. Now you got to tell the TI what to put in L2. And that's where the binomial part comes in. What is the chance of someone saying yes?
0.18.
That's where the 18% comes from. Somewhere in the problems, you need to see that probability lined out for you. Somewhere in that problem, you're going to see a percentage, and that percentage is going to tell you what this probability is. And that's that line right there. Based on past years, she knows that 18% of students are going to say yes. So there's where your 0.18 comes from. 0.18. So this is the 0.9 for chickens. This was the 0.5 for flipping a coin and things like that. Yeah, beautiful. All right, here we go. It's thinking. It's now done. You now have everything you need in your stat lists. So here's your stat, here's your editor, and there's your distribution. Here's the number of people out of 12 that say yes, and here's the chance of that many people saying yes. What's the chance that nobody says yes? Pretty good, actually. Only 18% of people say yes. That's closer to 0 than it is to 100%. So there's a pretty good shot, almost 10% are going to have 12 people that all say no. What's the most common outcome?
2.
Looks like 2. Could we have predicted that without even running this entire chart thing? The binomial is the only time you can do this,
yes.
Just so you know. You can, couldn't you? Because you asked 12 people, and there's an 18% chance that they're going to say yes. So roughly 18% of the 12 are going to say yes, right? So what's that going to be?
2.
That's a little bit right around 2. If you need more accuracy, you can just, well, here's 2 ways you can do it. You can do 12 times 0.18 to get you 2.16. That's one way to do it. But that makes you memorize a formula. And I'm not entirely convinced I want you to memorize a formula. Another way to get the average would be just to what? Like you've been doing since week 2, week 3. Run your 1-var stats. You run your 1-var stats and you're going to see it. Make sure you do L1 and L2. There's your average, 2.16. Yeah, plus or minus the 1.33. That's not important for this problem, though. It's too skewed. Make sense? So there's your average, and you just answered part D. How many would you expect to attend? About 2. About 2, because that's roughly 18% of 12. On average. On average. Now, the distribution shows us that if you ask 12 people, lots of different things can happen. But on average, you're going to get 2 people per 12 over time, long run. Renee, go. Please. No. Oh, you didn't? I'm sorry. I thought you did. Now, the next 2 questions we can still get from this table. Find the chance at most 4 students will attend. What does that mean? At most 4. What does at most 4 mean? All of them up to and including 4, yeah? So basically 4 or fewer. No more than 4. So we'd have to, John, say it again?
Max? I was just saying the maximum to attend is going to be the 4 or less.
Oh, got you. You said it different. I see what you're saying, John. I see what you're saying.
Yeah.
So basically, that's what we need to worry about right there, yeah? Add those up, you got your answer. That's the chance. Because this goes back to your first project now. At most 4 can be written using the word or, can it? At most 4 means either nobody comes, or 1, or 2, or 3, or 4. So you can use that old idea of addition to figure it out. So what's it going to be? That's about 9, 24, 33, that's going to be like 62, 83, 94, about 94%-ish. The answer's in the book, so you can back check it. I'm getting about 94%. So, I mean, that's 19 times out of 20, you're going to get no more than 4 people. Why would you care about that? If you could say 95% of the time I get no more than 4 people, why would you care about that? If, say, you were the organizer of this event.
Gotta fill 20.
Well, that's the mathematical reason. But, Andrea?
Then, I mean, are you reaching enough people? Is there a point? Are you like, are your costs outweighing your benefits?
At 95% certainty that you're getting no more than 4 people out of 12, in other words, no more than 1/3 of your intended audience, should you be marketing this thing better? Right? Should you be marketing? I mean, we can say that from the 18% in the beginning. 18% is pretty low. Maybe we want that higher. Maybe we want that up around 90%. Or maybe that's a little unrealistic. I mean, this is probably happening in a college, and it's always tricky. That video, for example, I marketed that thing for three weeks to get people to come out to and be in. And I got a great turn. I got 50 people to turn out. But there's 500 people that work at the school. So I got 10% of the population to come out and be in the video, and I marketed the hell out of it. So then the question is, how do I reach more? Another great question, and for different time for conversation. But yes, good. But suppose this year, you're planning this year's activities. Why would this be important? I love that answer, by the way, Andrea. Thank you.
So you can plan for it.
So you can plan for it. You don't necessarily have to expect 12 people. If you expect no more than 95% of the time, you may be able to get a smaller room, less food, smaller budget, save money for other stuff. You see what I'm getting at? You can actually use this for planning purposes as well. Good? Good. Renee, go.
Would you use it to figure out how many people have in a sample?
You can do that. 244 is a big part of it, actually. Yeah, 244. Renee's question is sample size. Can we use that percentage to decide anything about a sample size draw? Yes. It's called the power of a test. Very, very important. Your last project, it ties into your last project. Your last project due in week 10 is about false positives and false negatives. False positives and false negatives. Now, there are true positives and true negatives and false positives and false negatives. And if you're basing a study based on something like this, where you're interviewing folks and getting a percentage back, you might think that, okay, I'm going to change my marketing plan. I'm going to go with Andre. I'm going to change my marketing plan. I'm going to drive that. I want to double that. I want 36% at least, if not more, that are going to come to Tech next year, right? And you can run a marketing plan and then do a sample and ask people, and they're going to come back with results, and you go, look at that. My sample came back at 42%, therefore I am convinced I'm going to have twice as many people at Tech next year. You could be wrong. That could be a false positive. In other words, it looks like more people are going to come, and they don't. That's a false positive. Or you could run the exact same thing. Bump up the marketing campaign, ask a bunch of people, comes back 18%. And you go, oh, well, I guess it's going to be the same turnout as last year. And then what happens? You get slammed. That's a false negative, because you didn't think anything changed, and then it did underlying. So you can miss things. And that's where your sample size calculation comes in. It's a way to alter a sample size to say, okay, if I want to see it double, how many people do I have to survey to make sure I'm going to see it double? Does that make sense? But that takes way more than 2 weeks to get into. We'll get that in 244, I promise you. Good? Jamie? Yes?
For E11, would you do the same thing?
I don't know. Let's finish this and then go to E11.
Okay.
I don't know where E11 is. No, good question, good question. This is off now. Let's look at F real quick. What's the chance more than 2 students will attend? Okay, so now we're here. What's more than 2?
3
4?
through 11 through 12.
3 through 12, yeah? So we're going to have to add up all this, essentially. Or not. We can use an old trick, right, Angie? Can we use an old trick from your first project? Add these 3 up and take it away from, look at you guys. I'm so proud. Yeah. Add those up, take them away from 1. Whatever's left has to be 3 through 12. Yeah. Use the distribution wisely, because you know it sums to 100%. Fair enough? Yeah, there you go. It makes sense now, Shane. Yeah, so you ask a very good question, because when you're trying to assume that something is binomial, then you have to look for 2 numbers. First of all, how many times did you run the trial? And what's the chance of success on any given trial? And both of them are in there. Sometimes they get a little hidden. Sometimes they get a little buried, but they're all in there. Cool? Thank you, thank you. Did anybody balk at this one and say it might not be binomial because you're sampling the students without replacement? And we do that all the time in here with chickens and with the red-green color blindness, but we say that because the population is so large and we're only drawing 12, that it's binomial enough. So what are we assuming about the size of the school? We're assuming the school's pretty big, right? We're assuming the school is big enough so that pulling 12 people out of it doesn't change the percentage, that 18% as we go. I think that's a fair assumption. But if it's a tiny school, I noticed this more when I moved out west. On the East Coast, there's so much population density where I lived that all the schools are huge. The classes have 50 kids in them and everybody's wired. And I moved out here and for the first place that offered me a job was Cascades Academy, and they said, congratulations, you can have the job here. I'm like, sweet, tell me about it. They're like, well, you have to teach kindergarten through 12th grade. And I'm like, time out. What? And they're like, we only have 36 students. I'm like, in each class? They said, no, total. I'm like, time out. Tell me more about your school. And there's like 3 kids in a class. There's like 3 kindergartners, 2 first graders, 3 second graders.
No first grader.
There we go, you're a first grader, beautiful. I mean, I had you. But the thing is that a school that small, if you draw 12 people out of 36, that's a third of the school. It's no longer 18% anymore in each draw. But that's an extreme case. But if that's the case, then you don't use the binomial, you use something else called hypergeometric. But we'll come back to that. Make sense? Good, thank you, Shayna. Jamie asked about E11. Let's toe down and take a look at that. Let's start and stop though.